Deep beneath southwestern Poland, in the Lower Silesia region, lies one of the planet's largest copper deposits. 1.5 billion tons of ore, 21 million tons of pure copper, enough reserves to last several more decades. Here, at depths reaching 4,600 feet, that's 140 stories down, operates the company KGHM Polska Miedź. Every year, it brings to the surface nearly 400,000 tons of copper, the only European mine in the global top 10 of largest copper producers. But that's not all. Along the way, they extract silver in such volumes that KGHM is the world's #1 producer of this metal. Gold, nickel, lead, rhenium, selenium, platinum from a single ore. Today, we're descending into this underground world, following copper's entire journey, from black rock nearly a mile down to shining wire, without which every factory, every phone, and every electric vehicle on the planet would grind to a halt. Poland's copper story begins in 1957. Geologist Jan Wijekowski was drilling a borehole near the town of Złotorysia when he hit an ore body so massive he didn't trust his own instruments at first. 43 miles long, 12 miles wide, the Legnica-Głogów copper belt turned out to be one of the largest deposits on Earth. By 1961, they'd sunk the first shaft. Today there are 3, Rudna, Lubin, and Polkowice-Sieroszowice. Rudna is the biggest. Its levels stretch underground across 36 square miles. That's roughly the entire center of Warsaw. The ore sits in 3 types of rock: sandstone, shale, and dolomite. Layers of copper mineralization, chalcocite, bornite, chalcopyrite, plunge downward like pages of a giant book, tilted at an angle to the horizon. Average ore body thickness, 3 to 10 feet. Copper content, 1.5%. Which means, to get 1 ton of metal, you need to haul up and process 67 tons of rock. Before mining can start on a new level, you need to sink shafts, vertical tunnels about 26 feet across. Here's where things get tricky: aquifers. When they drilled the first shafts back in the 60s, the rock was saturated with water under massive pressure. Standard drilling? Instant flooding. KGHM engineers developed a unique solution: freeze the rock solid. Around the future shaft, they drilled 8-inch boreholes in a circle, pumped in calcium chloride chilled to -22 Fahrenheit. 3 to 6 months later, the water in the rock around the shaft turned to ice, creating an ice wall several yards thick. Only then could they start drilling the shaft. Today, the new GG1 shaft in Polkowice, commissioned in 2024. Depth, 4,416 feet. That's the deepest mining structure in Poland and the largest underground project in European non-ferrous metallurgy. At 4,400 feet down, the rock temperature hits 104 degrees Fahrenheit. Without air conditioning, people wouldn't survive. KGHM built a massive underground cooling system. Refrigeration units pumping over 50 megawatts chill air down through ventilation shafts. Miners work at the face in temperatures around 82 to 86 degrees. The mining method? Room and pillar. Miners use specialized low-profile drill rigs, just 5 feet tall because the ore seam is the same thickness, to drill holes into the roof and walls of the working face. These holes, up to 13 feet deep, get packed with explosives. After the blast, rock collapses into the chamber. But it's not that simple. Rock pressure at 4,400 feet? That's 8,000 tons per square meter. Rock under that kind of pressure behaves unpredictably. KGHM created a unique seismic monitoring system. Hundreds of sensors throughout the mine detect the slightest tremors. A computer analyzes data in real time and warns of rock burst risk minutes before it happens. Over 60 years, this system has saved thousands of lives. The blasted ore is loaded by load haul dump machines, massive diesel-powered scoops with remote control. The bucket capacity is 10 cubic meters, about 25 tons of ore in a single scoop. The machine hauls the ore to a transfer point, where it's dumped into an ore pass, a vertical shaft 5 feet in diameter, through which the ore falls downward by gravity to a level with conveyors. The conveyor system in the Rudna mine spans over 300 miles of belts. The ore moves toward the shafts at 13 feet per second. At the base of the hoist shaft, it accumulates in a bin with a capacity of 1,000 tons, from which it's loaded in batches into the hoisting vessel, the skip. The skip, with a 30-ton capacity, rockets upward at 52 feet per second. That's almost 40 miles an hour. The climb from a depth of 3,300 feet takes 70 seconds. Each hoist shaft delivers between 25 and 30,000 tons of ore to the surface every day. On the surface, the ore is hauled to the processing plant. Here's where the first bit of magic happens. Copper content in the ore? 1.5%. That's way too low for smelting. We need to bump it up to 23%. The ore gets crushed in cone crushers down to half-inch chunks. Then it heads into ball mills, horizontal drums about 16 feet across packed with steel balls. The drum spins, the balls tumble, and they grind the ore into powder, particles smaller than 0.04 inches. This finely ground slurry gets pumped into flotation machines, rectangular tanks holding up to 26,000 gallons each. Special reagents get added, xanthates and frothing agents. Compressed air bubbles up through the slurry from below, creating millions of tiny bubbles. The reagents make the surface of copper minerals hydrophobic. They repel water. Air bubbles stick to the copper particles and drag them to the surface as foam. The waste rock sinks to the bottom. Scrapers skim off the foam. That's copper concentrate with 23% copper content. One flotation cycle pulls out 88 to 90% of the copper from the ore. The concentrate ships to the copper smelter in Głogów, one of KGHM's 2 plants. They use a single-stage flash smelting technology. The concentrate gets dried to 0.3% moisture and fed through a burner into the smelting furnace shaft. At the same time, they blast oxygen in. Not air, but pure industrial oxygen at 95% purity. Suspended concentrate particles ignite in the oxygen stream instantly, in fractions of a second. Temperature in the reaction shaft hits 2,550 degrees Fahrenheit. Copper sulfides oxidize, releasing massive amounts of heat. The reaction's nearly self-sustaining, requiring very little additional fuel. At the bottom of the settling chamber, 2 melts separate. Matte, a molten copper sulfide at 65% copper content, and slag, a silicate melt with waste rock. The slag gets drained and processed separately. They still extract copper from it using additional flotation. The matte goes to the converter. Oxygen gets blown into the converter with the molten matte. A second oxidation happens. Sulfur burns off. Iron oxidizes and shifts into slag. What's left is blister copper, 98.5% pure. But we're not done yet. The blister copper gets cast into anodes, plates 3 feet wide, 3 feet tall, 2 inches thick, weighing 660 pounds each. They're hauled to the Electrolytic refining shop. Here, tanks 20 feet long, filled with a solution of copper sulfate and sulfuric acid. Into each tank they hang alternating anodes and thin stainless steel starter sheets. A direct current runs through the solution, about 60 amps per square foot. Copper dissolves from the anode, travels through the electrolyte, and deposits onto the starter sheet. After 12 to 14 days, a cathode builds up on the sheet, a plate of pure copper weighing 130 pounds at 99.99% metal content. That's grade A, the highest category of exchange copper on the London Metal Exchange. Everything else, gold, silver, platinum, palladium, selenium, settles to the bottom of the tank as anode slime. It gets collected and sent to the precious metal shop. From this slime, KGHM pulls 1,200 tons of silver every year, more than any other producer in the world. Some of the cathodes get remelted and rolled at the Sardinia plant into copper wire rod, wire about 1/3 of an inch in diameter. This is the key intermediate product for the cable industry. The wire rod gets wound into coils weighing 5 tons and ships out to cable factories across Europe. All told, nearly 400,000 tons of copper flow from Polish mines through all these stages every year. 24 million tons of ore hauled up from below. 34,000 workers. All of it, for a metal without which modern civilization simply couldn't exist. Where does all this copper go? First, power. Every cable, every wire, every transformer winding, copper. The entire electrical infrastructure of the planet runs on this metal. Without it, you can't transmit a single watt of energy from the power plant to your outlet. Second, construction. Every modern home hides between 220 and 440 pounds of copper pipes and wiring. Water supply systems, heating, air conditioning, copper everywhere. Third, electronics. Your smartphone contains about 1/2 ounce of copper. Not much? Except the world sells 1.5 billion phones a year. Computers, servers, circuit boards, the copper traces are visible to the naked eye. Fourth, transportation. A typical gas-powered car contains 51 pounds of copper. An electric vehicle? 132 to 183 pounds. Power cables, motor windings, battery bus bars. Fifth, renewable energy. One 3-megawatt wind turbine uses about 4 tons of copper. Solar panels, copper bus bars collecting current. The world is shifting to green energy, and every step of that transition increases copper demand. Forecasts predict demand will grow 70% by 2050, which means those KGHM mines beneath Polish soil will keep running nonstop for decades to come. I'm standing at the shaft of the Rudna mine. The hoist roars as it delivers another skip full of ore. 30 tons of black rock that'll become wires inside Danish wind turbines in a few weeks. Cables under the English Channel. Windings in Berlin subway motors. Connectors and servers storing your cloud photos. Copper is the blood of technological civilization. It flows invisibly through everything that runs on electricity. And every single gram of this blood begins its journey right here, in the darkness beneath Polish soil, where people in hard hats work a mile underground to make our lives possible. If you found this interesting, hit that like button. Drop a comment and let me know. Did you know Poland is the world leader in silver production? And subscribe. This is where we open up the industries behind every object in your life.
But an 80,000-ton press isn't just about aviation and space, it's about energy. Massive shafts for hydro turbines, rotors for nuclear reactors, high-pressure housings, all of this demands single-piece forgings of monstrous proportions. Picture a hydro turbine shaft 50 feet long and over 6 feet in diameter. Its weight, more than 100 tons. You can only forge a component like that on a super powerful press. The blank gets heated in a furnace the size of a house, then a crane transfers it onto the press platen, and in just a few strikes, it's shaped into form. Each strike, 80,000 tons of force molding the metal, densifying its structure, squeezing out internal defects. After forging, the part cools slowly, then undergoes heat treatment and machining, but the foundation of its strength, that's laid right there on the press. 80,000 tons. Picture a force that could crush 10 tanks at once. A machine tall as a 10-story building that transforms a red-hot steel mass weighing hundreds of tons into a flat panel like it's Play-Doh. This isn't science fiction. It's the world's most powerful forging press, operating in China since 2013. 80,000 tons of pressure. That's more than the weight of 50,000 cars crashing down on a piece of metal the size of a table. Why did humanity need such monstrous machines? What secrets hide in their history from the Cold War? How did the USSR create a 75,000-ton monster and the US answer with a 50,000-ton press? You'll discover how these metallurgical giants were born, how this inhuman force works, and what can be done under such pressure. Watch till the end. The finale reveals the scale of what humanity creates. The story of giant forging presses didn't start with peaceful purposes. It started with the Cold War arms race. In the late 40s and early 50s, aviation and rocketry demanded fundamentally new solutions. Aircraft were getting bigger, faster, flying higher. Rockets grew in size. And all of this required enormous single-piece components made from high-strength alloys: titanium wing spars, aluminum fuselage panels, steel rocket engine parts. Welding these components together from multiple pieces weakened the structure. Welded seams were vulnerable under load and vibration. What was needed was a technology capable of forging a giant part as a single piece, no seams. That's how the idea of ultra-powerful hydraulic presses was born. The United States understood this first and built several presses in the 50s, capable of exerting up to 50,000 tons of force. The Soviet Union wasn't about to be left behind. At the height of the space race and the arms race, the USSR built a 75,000-ton forging press, an absolute record at the time. The giant machine stood in the factory floor like a metal cathedral, dozens of meters tall, hundreds of tons of structure, hydraulic cylinders as thick as a human body. This press allowed the Soviet Union to stamp out parts for rockets, submarines, and aircraft on a scale that was previously impossible. A solid titanium component several meters long, no longer a dream, but reality. 75,000 tons of force meant that metal of any hardness became pliable material. The Cold War fueled technological progress, and these forging giants were one of its symbols. For decades, these presses remained the pinnacle of engineering. But in 2013, China shattered all records. At one of their metallurgical plants, they fired up a hydraulic press with a force of 80,000 tons. 80,000 tons? That's a force that's hard to wrap your head around. It's the weight of a major ocean liner crashing down on an area the size of a dining table, or pressure equivalent to 50,000 cars stacked on top of each other. The scale of this press is mind-blowing, as tall as a 10-story apartment building, weighing thousands of tons of steel and cast iron, with massive hydraulic systems capable of generating this monstrous force. This press didn't just break a record, it opened up a whole new era of possibilities. Now you can stamp out parts of sizes that used to be considered impossible. Panels for jumbo jets, components for space rockets, reactor equipment, all of this became achievable thanks to this machine. How does a giant like this work? The foundation is hydraulics. Picture massive cylinders filled with oil under monstrous pressure. When pressurized oil flows into the cylinder, the piston starts to move. But this isn't your ordinary piston. Its diameter measures in yards, and its stroke spans dozens of yards. Slowly, but with unimaginable force, the piston descends to where a glowing metal workpiece sits on a massive plate. The workpiece weighs hundreds of tons, a huge ingot of steel, titanium, or aluminum, heated to around 2200 degrees. The metal glows bright orange, radiating unbearable heat. The shop floor fills with the roar of hydraulics, the smell of hot metal and oil. And then, the upper plate of the press begins its descent. Slowly, almost ceremonially. But behind that calm lies 80,000 tons of force. Contact. The upper plate of the press touches the red-hot blank, and the miracle of deformation begins. Metal that's hard as rock at room temperature starts flowing like thick paste under this kind of pressure. 80,000 tons don't give the metal a choice. The blank flattens, spreads outward, takes the shape of the die. A thick ingot becomes a flat panel or a complex three-dimensional part. The process is accompanied by deafening thunder. The metal cracks, groans. Excess material squeezes out, flowing to the sides in glowing streams. Temperature, pressure, force, all controlled by computers with millimeter precision. The slightest mistake and a multi-ton blank is ruined, or worse, the press itself can fail. But the operators know their craft. One stamping cycle takes minutes, but the result is a seamless part with perfect internal structure. Why does this matter so much? Because a single forged part is stronger than any welded structure. A weld seam is always a weak point. Under load, vibration, cyclic stress, that's where cracks start. In aviation or spaceflight, a crack means catastrophe. That's why major structural elements, aircraft wing spars, fuselage panels, landing gear components, rocket engine parts, must be one piece. A super heavy press can forge a titanium beam 30 feet long with no joints whatsoever, or an aluminum panel the size of half a Boeing wing, or a steel blank for reactor equipment weighing 400,000 pounds. Parts like these used to be welded together from dozens of pieces. Now they're made in one press stroke. It's a revolution in manufacturing.
China didn't build this press by accident. The country is aggressively developing its aviation industry, space program, and nuclear power. All of this demands technologies that were previously only available to the US and Russia. An 80,000-ton press is a declaration of technological leadership. Now China can manufacture components it used to have to buy from abroad or settle for smaller dimensions. This is strategic independence. When you've got a press like this, you can build your own aircraft, your own rockets, your own reactors without relying on someone else's technology. It's no coincidence that information about the exact specs and capabilities of this press is tightly controlled. This isn't just manufacturing equipment, it's an element of national security and technological sovereignty. There are only a handful of these presses in the world. Russia has kept its Soviet-era 75,000-ton giants, still running in defense plants today. The US operates its 50,000-ton machines, built back in the 50s and 60s. China now leads with 80,000 tons. There are projects for even more powerful presses, 100,000 tons and beyond. But each of these machines represents a colossal investment. Building a super heavy press costs hundreds of millions of dollars. You need a special foundation that goes dozens of feet into the ground. You need massive hydraulic systems, furnaces to heat the billets, cranes with lifting capacities in the hundreds of tons. It's an entire complex covering the area of a football field. But the payoff is worth it, the ability to manufacture parts that nobody else can. And just like that, through the Cold War, through the technology race between superpowers, through decades of engineering development, humanity arrived at the 80,000-ton press. This isn't just a machine, it's a symbol that we've learned to dominate matter with a force comparable to geological processes. When 80,000 tons come crashing down on white-hot metal, it's like watching the Earth's crust crumple into mountains under tectonic plates. Except here, this process is controlled by humans. Every part that comes out of a press like this carries the imprint of unimaginable force and precision. Planes fly, rockets shoot into space, reactors generate power, and behind all of it stand these giant presses, crushing metal like Play-Doh. This is the story of how humanity learned to create the force of gods and use it to conquer the sky, space, and the atom.
What you're witnessing here is something that would have made our grandfathers stop dead in their tracks and stare in absolute wonder. This is the forging of a massive rolling mill shaft for a steel plant weighing 5,700 pounds. That's almost 3 tons of solid steel being shaped by pure force and principles that are centuries old. The process starts with a massive steel ingot that's been heated in a gas furnace to around 2,200 degrees Fahrenheit, hot enough to glow like a miniature sun. Back in the days when American steel mills dotted the landscape from Pittsburgh to Gary, Indiana, this kind of work was the backbone of our industrial might. The forging press you're seeing here is a modern hydraulic giant capable of exerting thousands of tons of pressure. But the fundamental process hasn't changed since blacksmiths were shoeing horses on Main Street. Watch closely as the glowing workpiece gets positioned under the press. The operators, and these folks are true craftsmen, use overhead cranes and manipulators to rotate and position the workpiece with incredible precision. Every press strike, every controlled squeeze is carefully calculated. They're not just hammering hot metal, they're restructuring the grain structure of the steel, eliminating internal voids and creating a component that'll eventually face enormous forces in the rolling mill. The shaft gets worked from multiple angles, gradually taking shape. Between each pressing operation, the team repositions the workpiece, sometimes returning it to the furnace to maintain that critical working temperature. This dance between heat and pressure goes on for hours. The hydraulic press moves with deliberate force, almost gently despite its massive power. Around 5,000 to 10,000 tons of pressure compacts the steel's crystalline structure into something far stronger than the original ingot could ever be. What's fascinating is how this forged shaft will serve in a steel mill, helping shape other steel products. It's a beautiful cycle. Metal processing metal, and these shafts can last for years under extreme conditions. Today's technology, precise temperature control, computer-controlled press cycles, metallurgical analysis, ensures consistency our ancestors could only dream of. But the soul of the process remains unchanged. Heat, pressure, and the skilled hands of craftsmen who understand steel like old friends. Now here's something that combines brute force with surprising delicacy. The process of coiling a 2-inch spring bar. If you've ever wondered how these massive industrial springs are made, the ones that control freight train suspension or support heavy machinery, you're about to get a lesson. The process starts with raw stock, in this case a solid 2-inch diameter rod of heat-treated spring steel. This isn't ordinary metal. It's been precisely engineered to have the exact balance of hardness and flexibility. Too hard, and it'll snap like a pretzel. Too soft, and it won't spring back properly. Watch as the rod feeds into the coiling machine. The machine grabs one end, while a massive rotating mandrel, essentially a former, begins bending the rod around its circumference. The force required here is substantial. We're talking about permanently deforming 2-inch steel, which demands hydraulic power in the range of several hundred tons. The mandrel size determines the spring's inner diameter, and precision here is critical. As the coiling progresses, you'll notice how smoothly the rod bends despite its thickness. This is achieved through controlled feed rates and constant pressure. The machine maintains tension while rotating, creating consistent spacing between coils. Back in the 30s and 40s, this kind of work was done by hand with tremendous effort, using heat and mechanical advantage. Modern CNC systems can produce springs with tolerances measured in thousandths of an inch. What you're seeing here is one of the most reliable welding processes ever developed: submerged arc welding. This technique has been joining heavy steel since the 1930s. Here's what makes this process so special. Unlike stick welding, which your grandfather might have done in his garage, or even modern semi-automatic welding, submerged arc welding happens beneath a blanket of granulated flux. This flux, which looks almost like coarse sand, performs several critical functions. It shields the molten weld pool from atmospheric contamination, prevents oxidation, and actually contributes to the chemistry of the weld itself. The setup is mesmerizing. A continuously fed wire electrode runs through the welding head, and when it strikes an arc to the base metal, it melts both the electrode wire and the parent material, creating a deeply penetrating weld. But you can't see any of this happening because it's all taking place under that protective layer of flux. The flux melts on top, forming a protective slag that operators chip off later. Watch the welding head move along the joint. It's typically automated for consistency. The process can deposit weld metal at rates that would make a stick welder cry with envy, 10 to 50 pounds per hour depending on the setup. That's why submerged arc welding is the #1 choice for welding thick sections in shipbuilding, pressure vessel fabrication, and structural steelwork. The beauty of this process lies in its depth of penetration. Submerged arc welding can achieve full penetration welds on steel up to 3/4 of an inch thick in a single pass. Now, let's look at modern hot forging, a process that's adapted traditional forging techniques to produce complex automotive and industrial components at volumes that would have been unthinkable in the old days of small-batch artisanal blacksmithing. The process begins with steel blanks, which are cut to precise lengths and then fed into induction heating systems. Induction heating is one of those technologies that seems almost magical when you first encounter it. No flame, no combustion. But within seconds, a steel blank placed inside an induction coil glows cherry red, then orange, then that brilliant yellow-white that tells you it's ready for forging. Alternating current flowing through the coil creates a rapidly changing magnetic field, which induces electrical currents in the steel itself, and these currents generate heat through resistance. After heating to the optimal forging temperature, typically between 2000 and 2300 degrees Fahrenheit, depending on the steel grade, the blank is transferred to the forging press. Sophisticated closed die forging is used, where the hot steel is placed between two die halves that contain the negative impression of the desired part. When these dies come together with thousands of tons of force, the steel has nowhere to go but to fill every contour of that cavity. Excess material, called flash, gets squeezed out around the edges and is later trimmed off. What's remarkable is the speed and precision of modern forging presses. Machines that can complete a forging cycle in just a few seconds, yet achieve dimensional tolerances that would have required extensive machining in the past. Sometimes you need to bend metal that's so big it seems almost impossible, and that's exactly what a horizontal bending press specializes in, forming massive pipes that can be several feet in diameter. The problem with bending large pipes is avoiding what we call wrinkling on the inside radius and tearing on the outside radius. The system solves this through controlled hydraulic pressure applied by a precisely formed die that supports the pipe during the bending process. Watch as the massive pipe gets positioned in the machine. That positioning alone requires overhead cranes and careful alignment. The bending die, often weighing several tons itself, presses against the pipe while it's supported at both ends. The hydraulic system applies hundreds of tons of force, gradually bending the pipe through the desired angle. Even with pipes this size, the bend radius, angle, and final dimensions can be controlled to surprisingly tight tolerances. These bent pipes end up in industrial piping systems, structural applications, and even shipbuilding. We're watching the cutting of a heavy railroad rail, 47 kilograms per meter, which translates to roughly 95 pounds per yard, using oxy-fuel cutting with propane. The oxy-propane torch system operates on a principle that's elegantly simple, yet demands real skill to execute properly. The propane flame, mixed with oxygen in the torch's preheat nozzles, heats a spot on the steel to ignition temperature, around 1600 degrees Fahrenheit for steel. Once that critical temperature is reached, a stream of pure oxygen under high pressure is introduced through the cutting nozzle. Here's the beautiful part. The oxygen doesn't melt the steel, it actually oxidizes it. The steel burns in the oxygen stream, and the force of that oxygen jet blows the molten iron oxide out of the cut, creating the kerf. The operator maintains a specific distance from the workpiece, the gap between the torch tip and the work surface, typically around 1/8 to 1/4 inch. Too close, and the tip will clog with splatter. Too far, and the cut becomes ragged. For cutting rail, you'll notice the torch follows the rail's profile. The rail has this characteristic mushroom shape: wide base, narrow web, and heavy head on top. Each section has different thickness, so cutting speed must be adjusted accordingly. We're now entering the realm of precision machining, where tolerances are measured in 10,000ths of an inch, and programming is just as critical as the actual technique. What you're witnessing is CNC milling of optical chuck jaws, programmed using CAM software, and this represents the perfect marriage of computer manufacturing and skilled craftsmanship. The process begins in the CAM software. A programmer working from engineering drawings creates a three-dimensional model of the chuck jaw, then generates the tool paths that will machine it. The program calculates optimal cutting strategies, selecting appropriate tools, determining feed rates and spindle speeds, and simulating the entire process virtually to catch any potential collisions or errors before a single chip is cut. Watch the CNC mill executing these programmed tool paths. This is likely a high-precision vertical machining center, equipped with a spindle that can rotate at 10,000 RPM or more while maintaining accuracy. Instead of plunging straight down, the tool follows spiral and trochoidal paths that maintain constant chip load and reduce tool wear. Notice the surface finish developing on the chuck jaw faces. These are critical contact surfaces that will grip workpieces, and they must be flat within microns and properly finished to avoid damaging delicate components. The float glass process you're watching, one of those manufacturing breakthroughs that completely transformed the industry. And remarkably, the core principle hasn't changed, since it was invented back in the 1950s. Here's how this incredible process works. Molten glass, heated to around 2000 degrees Fahrenheit, flows continuously from the furnace onto the surface of a molten tin bath. The glass literally floats on the tin, spreading under gravity and surface tension, forming a ribbon with parallel surfaces and uniform thickness. Watch as the glass ribbon advances through the tin bath. Temperature is carefully controlled, gradually cooling as the glass moves forward. This controlled cooling, called annealing, is critical. It relieves internal stresses that would otherwise cause the glass to crack or shatter during cutting or installation. As the glass exits the tin bath, it's cool enough to be supported by rollers entering what's called a layer, a long cooling tunnel where temperature continues to drop under precise control. The glass emerges at room temperature, perfectly flat with optical clarity that would have been impossible to achieve consistently using the old methods of sheet glass production. The production line can create thousands of square feet of glass daily, all with consistent quality. The ribbon is then cut to size, inspected, and prepared for further processing like tempering or coating.